Very good morning, students. Today we are going to discuss about the thermal conductivity chapter from transport phenomena. Already we discussed about the theory of thermal conductivity of gases at low density with help of the kinetic theory of gases and the different terms which used in kinetic theory. We have already derived the equation for thermal conductivity. We consider the terms like mean molecular velocity u bar, all collision frequency z is equal to 1 by 4 n u bar, mean free path lambda, and we also consider the distance traveled by the molecules after its last collision a. We compare these terms with respect to the kinetic theory and the thermal conductivity, and we written that 1 half mu square is equal to 3 by 2 kt. Then we discuss the velocity profile and we derive the equation, and finally we get the equation which is in terms of the thermal conductivity. So we compare this equation with Fourier's law of heat conduction and we derive this final equation last lecture. K is equal to minus 1 by d square root of k cube T by pi cube m, where small k is thermal conductivity of gases at low density, capital K is a Boltzmann constant, T is a temperature, D is the diameter of the molecule, and M is the mass of the molecule. So this is the one equation which is used to find out the thermal conductivity of low density gases. From above equation, it is proved that thermal conductivity is proportional to the square root of temperature. So whatever we discussed earlier, that thermal conductivity of gases increases with increase in a temperature. So it get proves. The second equation which is used to find out the thermal conductivity is Chapman-Enskog equation. So this is also the equation which is used for low density gases, and this is mainly used for monatomic, means for the pure gases. That equation is K is equal to 1.9891 10 raised to minus 4 square root of T by m upon sigma square into Ohm K, where K is the thermal conductivity of monatomic gases in calorie per meter seconds Kelvin, T is the temperature in degree Kelvin, m is a molecular weight, and sigma and Ohm K, these are called as a Lennard-Jones constant, and these values are in degree angstrom. We will consider these values as it is in degree angstrom. So already we discussed a Chapman-Enskog equation in Newton's law of viscosity when we discuss about the viscosity term. So there is also one Chapman-Enskog equation which is used to find out the viscosity. Here the Chapman-Enskog equation is used to find out the thermal conductivity. So both are the similar equations. We will discuss that Chapman-Enskog equation for viscosity during problems. One more equation which is used to find out the thermal conductivity of polyatomic gases at low density is Ekin's equation. So this is the Ekin's equation which is used to find out the thermal conductivity of gases. What is that equation? That is K is equal to Cp bar plus 5 by 4 R by m into viscosity, and this unit comes in joules per meter seconds Kelvin, where you know Cp bar is a heat capacity at constant pressure. It is in a joules per kg Kelvin. R is a gas constant. Its value you have to take it in joules per mole degree Kelvin if you want a same units. M is a molecular weight in kg by kg mole, and viscosity is nothing but kg per meter seconds. The same equation can be written in terms of 9.27. K is equal to Cp bar plus 5 by 4 into R bracket complete multiply by mu by m. If you write like this, then unit will comes as the previous one is calorie per meter seconds Kelvin. So we'll use this 9.27 equation to find out the thermal conductivity. So to know this, you are supposed to know the heat capacity at constant pressure. You are supposed to know the value of R, viscosity and molecular weight. So these are the terms used to find out the thermal conductivity by Ekin's equation. The last equation which is used to find out the thermal conductivity of liquids is called as a Bridgman equation. So this is called as a Bridgman equation. K is equal to 2.80 n bar by V bar bracket 2 raised to 3 K into Vs, where n bar is called as Avogadro's number. You are supposed to know the value of Avogadro's number along with the units. V bar is called as a molar volume. K is called Boltzmann constant, and Vs, that is new term, is called as a sonic velocity. So the sonic velocity term, which is obtained from the isothermal compressibility measurement that you have studied in the thermodynamics. So you have to remember what is the sonic velocity. Sonic velocity is square root of Cp by Cv into dou P by dou rho at constant temperature, where Cp by Cv is nearly unity for the liquids except at the critical value. I mean, generally we take Cp by Cv is 1, and dou P by dou rho at constant temperature, this term is obtained from the isothermal compressibility measurement. So this is how you can find out the viscosity, thermal conductivity of gases as well as liquids. So thermal conductivity of gases is found out by kinetic theory, Chapman's equation and Ekin's equation. Thermal conductivity of liquids is found out by the Bridgman equation. And finally about the thermal conductivity of solids. Thermal conductivity of solid is you have to measure experimentally. You cannot find out. So it is depends upon the many parameters. Like if you talk about the crystalline material, the phase and the crystalline size is very important. You see in amorphous solids. These amorphous solids needs the degree of molecular orientation, which is an important parameter. In case of porous solids, thermal conductivity is strongly depends upon the wide fraction, porosity, that is pore size, and what is the fluid content in the pores. So this is about the crystalline, amorphous and about the porous material. Also about the metals and non-metals. Metals are better heat conductor than the non-metals. Crystalline material conducts heat more readily than amorphous material, as you know. Dry porous solids are very poor conductor, and therefore they are used as a thermal insulations. So whatever the thermal insulations you have seen in industries, okay, generally they are the porous materials. The thermal conductivity of most pure metal decreases with increase in temperature. See here, the metals, the thermal conductivity decreases with increase in temperature, whereas thermal conductivity of non-metals increases with temperature. Alloys shows the intermediate behavior between these. For pure material, for pure metals, the thermal conductivity and electrical conductivity is related by this equation. K by Ke into T is equal to Lorentz number is equal to constant. So where K is thermal conductivity, Ke is called as electric conductivity. So thermal conductivity is different. It is related to the metals. Electric conductivity is different. How much current or electricity can be passed is given by electric conductivity. T is the temperature. Okay. And this equation is called as a Wiedemann-Franz-Lorentz equation. This Lorentz number generally vary between 22 to 29 raised to 10 raised to minus 9 whole square per Kelvin square. So this is for the pure metal at 0 degree Celsius. Okay, and it increases from 10 to 20% for per 1000 degrees Celsius being increased. So this is how we discuss about the thermal conductivity of solids. Now this chapter is over. In this chapter, we discuss about thermal conductivity of gases, liquids, solids. We discuss about the Fourier's law of heat conduction, how this will be a basic equation for the heat flow problems. We discuss about the theory of thermal conductivity of gases at low density with help of kinetic theory, and we derive the equation. We discuss Chapman's equation, Ekin's equation, then Bridgman equation and Lorentz number. So now we'll discuss few problems related to the thermal conductivity and we'll stop it here. So first problem is compute the thermal conductivity of argon at 100 degrees Celsius and 1 atmospheric pressure. So we know this is the problem related to the gases. So we have few options, but from the data you can realize which equation is to be used. Data given is molecular weight, sigma, ohm by K, epsilon by K, ohm K. So from this we can easily understand we can use a Chapman-Enskog equation. So we'll use that. K is equal to 1.9891 10 raised to minus 4 square root of T by M upon sigma square into ohm K. So all the values are given. You can directly find out the value of K. So put all the values of T, M, sigma square and ohm K and find out the value of K. K will be 502.36 into 10 raised to minus 7. It will be a calorie per centimeter second scale. Very important is you are supposed to know the unit consistency. The second problem is compute the thermal conductivity of NO, nitrogen oxide and CH4, methane at 300 Kelvin and atmospheric pressure. So here there are two gases, okay, but you can consider these are nothing but the gases of polyatomic. You can use a Ekin's equation. Is it right? So the value of viscosity is given and Cp bar is given. By Ekin's equation, you can find out the K for NO separately and K for methane separately. So K for NO is Cp bar into 5 by 4 plus 5 by 4 R mu by M. You can put the values of Cp bar, that values are given. R value you are supposed to know, R will be 1.987. It is a calorie per gram mole Kelvin. Value of viscosity is given and molecular weight is given. You can find out value of K for nitrogen oxide is 6.19 10 raised to minus 5 calorie per centimeter seconds Kelvin. For methane again use a same Ekin's equation. K is equal to Cp bar plus 5 by 4 into R bracket into mu by M. You can again find out value of K for methane in calorie per centimeter seconds Kelvin. Thus, you can use Ekin's equation to find out the thermal conductivity. We'll discuss one problem related to the thermal conductivity of liquids. So problem 9.4, the density of liquid CCl4 at 20 degrees Celsius and 1 atmosphere is 1.595 gram per centimeter cube. See here, the value of isothermal compressibility is given 1 by rho dou rho by dou P at constant temperature is equal to 90.7 10 raised to minus 6 atmosphere inverse. So from the data you know that we have to use the equation for thermal conductivity of liquids. So first of all, we'll calculate the value of isothermal compressibility. We'll find out dou P by dou rho. So what is the given is dou rho by dou P. So what we can write? We can write dou P by dou rho is equal to rho 1 upon rho into 1 by rho into dou rho by dou P at constant temperature. If you solve this, you will get value of dou P by dou rho. So you will get the value 6.912 atmosphere meter cube upon kg. But see, you cannot use atmosphere meter cube per kg because we are using that into a Bridgman's equation. So you have to find out that value in meter square per second square. So atmosphere you will get converted into Newton per meter square, and then you convert it into meter square per second square. You will get value of dou P by dou rho. Assuming Cp by Cv is 1, you can find out the sonic velocity by this equation. You will get sonic velocity is 836.79 meter per second. You can find out the molar volume by dividing molecular weight to the density. You will get value of V bar in meter cube per kilomole, and then you can put these values in a Bridgman equation and you can find out the thermal conductivity. So equation is K is equal to 2.80 N bar by V bar raised to 2 by 3 K into Vs. You know Avogadro's number is 6.023 10 raised to 10 with 3. Molar volume is calculated. You know value of Boltzmann constant, it is 1.3805 10 raised to minus 21. By knowing these values, you can find out the value of thermal conductivity. The last problem we will discuss again about the Chapman's-Enskog equation, because last problem the viscosity was given, but sometimes the value of viscosity is not given. So see, this is a interrelation between chapter 9 and now chapter 2. So read the problem. The molecular weight of oxygen is given, molar heat capacity is given, and you have to find out the viscosity and thermal conductivity of gases of oxygen. See here, means first you have to find out the viscosity and then you have to go for thermal conductivity. The value of sigma is given, kT by epsilon is given, and ohm mu is given. So what is the difference between ohm mu and ohm k? Keep in mind, if ohm mu is given, you have to use equation for viscosity, because these are the Lennard-Jones constants related to the finding the viscosity term. When ohm k is given, then you can use directly that values for finding the thermal conductivity. So ohm mu is given, so we'll use the equation of viscosity that we studied earlier, that is mu is equal to 2.6693 10 raised to minus 5 square root of m into t sigma square upon ohm mu. So put all the values, that all values are given to you. You can find out the viscosity first in gram per centimeter seconds. So see, you have to find out the viscosity from the equation that you studied in chapter 2. And now you can find out the thermal conductivity by another equation. You cannot use a Chapman-Enskog equation because value of ohm k is not given. So we'll use the Eakins equation is equal to K is equal to Cp bar plus 5 by 4 into R upon mu by M. All values are provided to you. You find out that values, put into the equation and find out the thermal conductivity. You will get equation 6.136 10 raised to minus 5 calorie per centimeter seconds Kelvin. So this is how we can find out the thermal conductivity of gases and liquids. So in this chapter we discuss everything about the thermal conductivity, about the Fourier's law, and about the thermal conductivity of liquids, gases and solids. So I think you understand everything about the thermal conductivity. In the next lecture we will discuss about the temperature distribution in solids and in laminar flow. Thank you.